когда говорят про код схемы, они как-то порой фиксируют некоторые мука и вес. Что это такое?
Это многочлен Гильберта.
Какой-то вектор в пространстве многочлена Гильберта?
Нет. Это просто многочлен Гильберта. Что? Нет, абсолютно не синонимы, но фиксация вектора Мукая это. Фиксация, да. Угу. Okay, so let me recall where we are. And first of all, we constructed some monad last time, and I explained its the etymology of the word monad in an absolutely wrong way. I said that monad is something about dress or garments. It's absolutely wrong. I was confused by some algae called chlamyda monada. And chlamyda is really some sort of garment in Greek. But monada, mona means single or unique. So the point is that it has just a unique middle cohomology and nothing else. Okay. So last time we constructed a monad for any torsion-free sheaf E on P2 with trivialization on the infinite line. And also with the second Chern class equal to n, and then we have n-dimensional vector space like this. So this monad like this. So this was in degree 1, in degree 0, in degree -1, and E was the middle cohomology. Okay, and well, this monad restricted to the plane, which is just the finite part of P2. Was given by the following formulas. So this was A equal to B1 minus Z1, B2 minus Z2, J. So it goes to V tensor, polynomials in two variables, Z1 and Z2. Okay, and here we had B that was negative B2 minus Z2, B1 minus Z1, I. Okay, and those B1, B2, I, J are so-called ADHM data, linear algebra data. And ADHM stands for Atiyah, Greenfield, Hitchin, Mannion. So those guys were solving some nonlinear mathematical physics equations, like instanton. Well, the solutions are called instantons, and they found these linear algebra data. Well, this. Okay, so you have a vector space V, you have two endomorphisms, B1, B2. We have another vector space W. And I never said that dimension of W is R, the rank of E. Pardon me? Where?
The arrow V. In monad. In monad.
Yes.
O1. Right.
O of 1, right. Thank you very much. Thank you very much.
Почему ограничение пучка I на P1 равно W на P1? Мы же доказали, что это ядро B по образу A. Как из этого следует, что это еще?
Well, it is part of data. The moduli problem we are solving is written down here.
Мы говорим, что это P1 степени R.
Right. This, okay. So we made some big work last time constructing this monad from resolution of diagonal on P2, and now we're in the process of proving that well, that this solves our initial problem. So we're proving the converse statement. So if we consider such data, then there is only one cohomology in the middle, and this cohomology is a torsion-free sheaf with this data. Also, I should write this equation somewhere. Okay, so we're proving, what was it, lemma or proposition? I forgot. Well, say lemma. That A. So we're looking at this monad, and we say that A is always injective. So we never have minus first cohomology. That A is fiber-wise surjective. Oh, sorry, injective. Well, if and only if the condition S2 holds true. And B is surjective. So there is no first cohomology if and only if the stability condition S1 holds true. Okay, this is everything we have to check. And let's check this. I will prove that even fiber-wise, A is almost everywhere injective. And then it follows that at the level of sheaves, A is necessarily injective. Because V tensor O whatever, everything embeds into V tensor the fraction, well, like C of P2, the field of rational functions, right? And now I will, well, here we have V plus W tensor O P2. It also embeds into V plus W tensor this field of fractions. And well, there is this A, there is this localized A. And since you know that A is almost everywhere fiber-wise injective, it means that it's injective at the generic point. So this is injective, and hence this is also injective for theory, right? Right, because this is generic point. You replaced your structure sheaf by the function at the generic point. Yeah.
And what does it imply? So, okay, at the generic point, it is injective.
Yes, but this embeds into its localization at generic point, right? So, since everything is injective, this must be injective as well. You can't have kernel here, otherwise you would have kernel here, or there. Okay. So
can it be that this map is fiber-wise? It is injective in each fiber except the generic point. But
no. Well, just generic point is the generic point. The name is meaningful. Yeah, it's just.
Could you explain how, by definition, how do we work out that that is almost everywhere fiber-wise injective? How does it imply that?
I mean, if you take general point Z1, Z2, then I will hopefully prove soon that at this point it's injective. And this Z1 is. It is, well. Just the Z1 and Z2 are. If it's true for general point, then it's absolutely true for generic point.
Could you please comment on this?
No. No. I refuse. Okay. So let's find the kernel of A at this particular point, Z1, Z2. So the kernel of A at Z equals Z1, Z2 is the set of vectors such that this thing vanishes. So first of all, B1V equals Z1V, B2V equals Z2V, and JV equals 0. Okay, and And you see that V is a common eigenvector of B1 and B2, right? And Z1, Z2 eigenvalues, right? And we only have finitely many eigenvalues, like n eigenvalues. So away from these eigenvalues, already this is impossible, even disregarding this J condition, right? So away from these eigenvalues, A is injective. Okay. So you asked about generic point. Just localize away from eigenvalues of B1, B2, and you are done. Then you are injective. That's the answer to your question. Now, so we proved A. What about B? Here we want to use the third condition as well. So suppose JV is 0. But then, from this equation, it means that I'm sorry, what I'm saying. Yeah, maybe I'm saying good thing. So from this condition, B1 and B2 are no, just what I want to say is that CV in V violates S2, right? If you remember what was S2, S2 was a condition that there was some subspace V second in V, and it was invariant with respect to B1, B2, and it was contained in the kernel of J. Okay, so just take this. It's invariant under B1, B2. It's contained in the kernel of J, so it does violate. But we want the equivalence here. Conversely, take the kernel of J, and on the kernel of J, to take maybe this V second inside the kernel of J. Then it is invariant under B1, B2. And since we are in the kernel of J, B1 and B2 commute, right? So B1 receded to V second, and B2 receded to V second, commute, and hence they have a common eigenvector V, and so there is a kernel. Okay, so these two conditions are indeed equivalent. So we proved B. Yeah. Now C. But maybe I want to erase something here. Yes.
Что мы доказали в последнем случае? Если у нас выполнены вот эти S2, то что?
So if S2 is violated, then there is this kernel. we've proved first that if there is this kernel, then S2 is violated, and conversely, if S2 is violated, then this kernel is non-trivial. But now I am stuck. What shall I erase? Maybe this.
Violated means нарушает.
Absolutely, yeah. It's the perfect interpretation. Okay, so C, and I claim that it's absolutely dual to B. So we have to check surjectivity fiber-wise. Yes. So for A, injectivity fiber-wise was a stronger condition than injectivity at the level of sheaves, but surjectivity at the level of sheaves is the same as just fiber-wise surjectivity. Okay, so this argument will be very similar to that argument, and formally we can just dualize. And then somehow S1 becomes S2. But maybe I have to recall what was S1. S1 was the existence of a subspace V prime invariant with respect to B1 and B2 and containing the image of I. So this was S2, this was S1. And these two conditions are dual. I mean, if you take B1 transposed, B2 transposed, I transposed, J transposed, and here you will have W dual, and here you will have V dual. Then there will be this J transposed, I transposed, and B1 transposed, B2 transposed. Then they will satisfy the same equation, and the conditions S1 and S2 will be swapped, and the surjectivity and injectivity will be also swapped. So just now apply B to these guys. Okay, so nothing changes. Okay? And the theorem is proved. So this is the great moment. Our big theorem is proved. So now we'll specialize to rank 1 case, to Hilbert scheme, but
Why?
yes.
To check that
Yes.
this bundle has
Yes.
second chain class equal to n.
Mm-hmm. But well, we did not really. If you do you know what is second Chern class?
No.
Yeah. So then we have absolutely no possibility to check this, right? But somehow, if you knew, then there is some way to. Well, there is a certain Chern character, a certain combination of Chern classes. Each Chern class, Ci, lives in ith cohomology, and then you can pair it to some fundamental class in homology of P2, and then you obtain just a number. But in general, it lives in cohomology. And this thing is inhomogeneous, so it lives in all the possible cohomology, but it has a nice property that this Chern class of E1 plus E2 is Chern class of E1 plus Chern class of E2. And it's also multiplicative. If you tensor, then so it's just a homomorphism from Grothendieck K group to the cohomology ring. Since it's additive, in fact, here you don't even have to take direct sum, it can be extension. So since it's additive, it makes sense for Euler characteristics, for complexes. And then you have just to add those three Chern characters to obtain the Chern character of the middle cohomology. And that's how you get this. Any other doubts? No, that's absolutely out of question. But I can give you my coat, jacket if you want. Shall I give you my jacket? Yes.
Is this relation that the restriction to one infinity is somehow restrictive? Because it seems strange.
This thing. So well, yes, on the one hand, it means that the first Chern class is 0. In this sense, it is very restrictive. On the other hand, it gives you some rigidity. So, well, because of this, you have the action of the group. No, I do have to erase something. Let me erase this. So you can change your trivialization, and it will give you a different object in your moduli problem. So the trivialization can be changed by the group GLW, and you obtain the action of this group GLW on the moduli space in question. So your moduli space remembers more than just isomorphism classes of vector bundles. Okay. So the section is non-trivial. Yeah, you might have the same isomorphism class of torsion-free sheaf or vector bundle, but with different trivialization, and you will get different point in the Gieseker moduli space. But if you disregard this extra datum rigidity, so in other words, if you try to consider the quotient modulo this action, then this will be something bad. It will be only a stack. It's not a variety. So this action is not free by any means. By the way, if we are going to waste our time, let's go back to the proof of theorem. And we considered some M0, if you remember, and there was an action of GLV, yeah, and then I claimed that this was the Gieseker moduli space MRN. And now this action was free. So since we are wasting our time, let's prove that this action is free. Yeah, so we have this data. We have the condition S1. Yeah, S2 is optional. If we impose S2 condition, then we obtain vector bundles, as opposed to torsion-free sheaves. But S1 always must hold true. And I ask why, if S1 is imposed, then it implies that GLV acts free, in a free manner. So I mean, if G applied to B1, B2, I, J is the same, B1, B2, I, J, then G is just identity. So any suggestions? Absolutely, yeah. But the action is, well, the only possible natural action. So it's the conjugation action on B. Then I is what? GI. And then G inverse. Yeah.
Так мы определили это.
Yeah, it's by definition, yeah. But you could possibly have no other definition. It's the only way to define this action. So,
Что мы хотим еще?
we want to prove this implication. Well, so yes.
Компонент подставить, решить.
Yeah, but how?
But do we know that B1 and B2 have mutual eigenvectors?
No, not necessarily, no. It was only some special property of kernel. But what we do know is that G restricted to the image of I, well, I of W, is identity, right? Because of this. Right? On the other hand, we know that the image of W generates the whole of V under the action of B1, B2. And so it implies that G restricted to the whole of V is identity. So G commutes with B1 and B2. B1 and B2 generate everything, so G is identity on everything. Okay?
What generated this?
But by the S1 stability condition, the image of W under I generates the whole of V under the action of B1, B2. Okay? So now the theorem is proved. And just one remark. That, as I mentioned, imposing this stability condition is the same as taking GIT quotient. And there are two ways to take GIT quotient with respect to determinant or inverse determinant character of GLV. But there's also a third possibility when we take the trivial character. So we take just the categorical quotient. So we can take whatever, U Rn. By definition, this is the categorical quotient, M modulo GLV. So by definition, this is the spectrum of the functions on M, invariant with respect to GLV. Okay, so we discussed this a year ago. This is the categorical quotient. Pardon me?
M is this MRN.
What is this M? This M is the closed subvariety in this vector space cut out by this equation.
With stability condition?
Without stability condition. So with stability condition, there is categorical quotient like this, or with opposite condition, there is another quotient. But without any stability condition, you just take all the solutions of this ADHM equation and the quotient out by GLV in this sense. Namely, take the spectrum of invariant functions. Right? And this is called the Uhlenbeck space. what I can say is that it is just the affinization of the moduli space of vector bundles. Affinization is just, again, the spectrum of the ring of functions on the moduli space of vector bundles.
Is it the general motion?
Affinization?
Yes.
Oh, yes. Yeah, for any scheme, you can consider this thing, but the caveat is that it can be infinitely generated. So you can take a nice Noetherian scheme, but the ring of functions will be infinitely generated. It can happen in principle. So you have to make sure this ring of function is finitely generated. In this case, it is finitely generated, and you obtain this Uhlenbeck space. And there is a natural morphism from MRN to the Uhlenbeck space. And this is the resolution of singularities. So, I mean, this Gieseker space is smooth, Uhlenbeck space is very singular, but they have the common open subspace classifying vector bundles. Yes. The moduli space of vector bundles. So where you impose both stability conditions and you have not just torsion-free sheaves, but vector bundles. Oh, yes. Yes, from this ADHM point of view, they correspond to quadruples with two stability conditions. But from modular point of view, it corresponds just to vector bundles among torsion-free sheaves.
Maybe stupid question.
Yes.
What's the difference between torsion-free sheaves and
Vector bundles. Well, we'll see in a moment for Hilbert's scheme, but for example, you can have the maximal ideal of point of the origin inside OA2. As we discussed a week ago, this is trivial one-dimensional bundle, and this thing is a subsheaf which is torsion-free, because any subsheaf is torsion-free, but it is not a line bundle. I mean, if we compute its fibers, all the fibers will be one-dimensional, but the fiber at the origin will be two-dimensional. And we discussed this last week, as far as I remember.
One general point we have, at point 0 we have two generators x, y.
Yes.
And at point 5, 5 we have just one generator 1.
Right, absolutely. Mm-hmm. And in fact, since we decided to waste all of our time, let me mention that for surfaces, S, well, for example, for P2, but for arbitrary surface, it's a local question. Given a torsion-free sheaf, E, there is the minimal vector bundle, well, locally free sheaf, E tilde, containing E, and such that the quotient is supported at a few points. So in particular, you see that any torsion-free sheaf on a surface is almost everywhere a vector bundle. Just that there are finitely many points where it has, sort of say, singularities. Well, like here, there is just the origin where the torsion-free sheaf had a singularity. And if you remember this argument when we computed the middle cohomology, it was to the same effect, that the points where your sheaf E was not locally free, where the common eigenvalues, where the eigenvalues of B1 and B2. Okay, so there were finitely many such points. Away from them, the middle cohomology was necessarily locally free, and only at those points you could possibly have singularities. Okay, so this is always so. And who is this E tilde? E tilde can be constructed in two ways. So one construction is E double dual. So it's local home from E dual to the structure sheaf, and E dual is local home from E to the structure sheaf. Okay, so you always have a tautological map from E double dual to from E, sorry, to E double dual, just sort of evaluation, and it's an embedding, and it's almost everywhere isomorphism. And another construction is just if you already somehow just take sufficiently many points out of your surface. So I claimed that there are only finitely many singularities. So if you remove all of them, well, let's say those suspicious points, and it's embedded into J, say U, into S, then this E tilde is just the push forward of E restricted to U. Sorry, the push forward of E restricted to U. Okay? So you throw away those bad points, and then you extend yeah, for example, if you had this maximal ideal at the origin inside O, the structure sheaf, then you remove the origin, you obtain the structure sheaf of the punctured plane, and then you push it forward to the whole plane, you obtain the structure sheaf of the whole plane, just by Hartogs theorem. Okay, it's sort of Hartogs theorem. But it doesn't work in higher dimension. It only works for dimension 2, this recipe.
And I have a question.
Yes?
If we are taking this maximal ideal, say for a line,
Yeah.
Then,
then you will have not a coherent sheaf, a quasi-coherent sheaf. If you push forward from an open subset of a curve, then you will get only quasi-coherent sheaf, right? Like.
I just wanted to try to imagine an example of a torsion-free sheaf with a suspicious divisor, not a set of points, but.
But divisors do not contribute, like with curves. With curves, any torsion-free sheaf was automatically locally free, if you remember. So the bad things happen only in codimension 2. And in codimension 2 exactly, they are not so bad. But starting from codimension 3, really bad things can happen. I mean, for example, you can have a vector bundle on three-dimensional space without a point that cannot be extended through this point in any way. Well, I mean, as a vector bundle. Okay. but for surfaces, the life is somewhat better. Okay, so these were all unnecessary comments, and now let's go back to yes.
С этим пучком эпсилон с волной, какой вывод мы что из этого следует? Мы построили, для чего мы его построили?
Maybe just to get some feeling about the torsion-free sheaves, what we're studying. The torsion-free sheaves are for surfaces are almost like vector bundles with some defects at finitely many points. Okay, so now we erase this. And we go back to our initial problem of constructing, computing the Hilbert scheme of endpoints on the affine plane. Endpoints of the affine plane. And now our proposition says that this is isomorphic to M1M. Okay. And the proof requires a lemma from linear algebra that we will skip. So it says that in this situation where when W is one-dimensional, so it's very specific for this situation. So if it's just one-dimensional, so that J is a functional and I is a vector. Yeah. So I, well, if you wish, I of 1 is a vector in V, and J is a functional on V.
А во всех этих конструкциях можно вместо комплексного поля какое-то другое поле рассматривать?
Oh yes, yes. So far we did not use any. It was characteristic free and everything. Yeah. Yeah, but maybe there will be some problem with Uhlenbeck space in this case. It will be just symmetric power, and you have to be well, to examine some caution with symmetric powers in fine characteristic. So in this situation, J restricted to this functional J restricted to whatever the subspace of V generated by B1, B2 from I of 1. So J restricted to this equals 0. So in particular, if we impose the stability condition S1, then it implies that J equals 0. Because everything is generated by B1 and B2. Okay, so this lemma we will not prove. It's just some advanced linear algebra. But there's a key difference between R equals 1 and R equals and R bigger than 1. So if R is bigger than 1, then the subspace M, cut out by this equation, is irreducible. Okay, and if R equals 1, then M has n plus 1 irreducible components. So one of them is specified by this stability condition. And then J equals 0. And there is some opposite one where we have the opposite stability condition S2, and then I equals 0. And in general, the component K is when the dimension of well, B1, B2, I of 1 is K. Okay? So we have this lemma, and now maybe let me erase it.
But how this lemma
Is proved.
no
What?
is used if J is 0, then B1, B2 can be used, and what?
Yeah, in particular, absolutely, yeah. So,
How
now I'm going to use it, if you don't mind. After I erase it, I will use it.
no, how we see irreducibility?
No, irreducibility is just a side remark.
Ah.
Again, we're wasting of your time, sorry. So I'm erasing this. Okay, so let's have a look at this monad. And in our particular case, W is one-dimensional. So this is just the structure. This component is just the structure sheaf.
Would you please briefly
Yes.
remind what connection between these spaces?
Which spaces?
Why W is one-dimensional, for example?
Just because the dimension of W is the generic rank, right? By the definition. I don't know what else can I say. Just. So this was C to the R. This was C to the N. Absolutely.
N of A2 is a model space of endpoints.
Absolutely, yes.
And what the connection with?
That's what I want to. That's what I want to explain right now. So this is our proposition. I am in the process of proving it.
Ah.
Sorry. Yeah. Well, maybe I don't have to copy this thing. That's why I didn't erase it. So in our case, this becomes just the structure sheaf, and J is 0, right? But since J is 0, it implies that, well, we know that the middle cohomology is some torsion-free sheaf of generic rank 1. And now we can, well, it is it is a subquotient of this middle sheaf, right? Namely, it is the kernel of B modulo the image of A. But the image of A, due to E, E is a subquotient of the middle thing. So it's V plus V tensor OA2 plus OA2. Okay, but due to the fact that J is 0, the image of A that were taking quotient modulo does not intersect this guy. So the projection onto this guy is well defined.
Not E is a subquotient, but maybe the restriction of E to A2 is a subquotient.
All right, thank you. Yes. Yes.
Yeah, that will be able to see.
So since J is 0, the projection from E, well, from the middle term, from this to A2, is well defined on E. And so I have this projection from E to E2. So indeed, E becomes a subsheaf here, a torsion-free subsheaf. So it's necessarily a sheaf of ideals. So E is a sheaf of ideals, well, of some subscheme. Of A2. Okay, and we have to check that this is really a bijection between all those possible E's and all those possible subschemes of A2. Okay? Yes. So everywhere, yeah. Everywhere restricted, yes. Okay. And now let's denote this sheaf like J of ideals. Now let's sort of say construct these bijections. So we construct the inverse bijection maybe from the sheaves of ideals to these guys. So we consider a function f on the plane, so just polynomials in two variables. And I claim that it lies in the ideal if and only if there are two vector valued functions, u1 of z and u2 of z in V with polynomial coefficients. So in other words, it's OA2 to the power n. Okay, such that this function multiplied by this generating vector I of 1 is z1 minus b1 times u1 of z plus z2 minus b2 times u2 of z. And this is just the definition, because our sheaf E is the kernel of B, well, modulo something projected to O. Okay, and here I write that it's a kernel, the kernel of B.
Is this n equals to
Yeah. N is this n? Yeah. All n are equal. Right.
Again, why is this projection restricted on E and then
Because we well, if it's not an embedding, it has some kernel, and then its kernel lies in the image of A, because this is the kernel of projection, right? The E is the cohomology, so it's something modulo the image of A, and the intersection of the image of A with this is empty, it's just zero.
okay, but the kernel will lie inside the kernel of B.
Yes.
Just assume you have a kernel of
Mhm.
projection restricted on E. Yeah.
Mhm.
The kernel is represented by some representative which lies in the kernel of B. Modulo the image of A, but lies in the kernel of B. So we have to study this.
Okay. Maybe let me say it this way. Mm, 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 sorry.
Maybe if we remove this O A2, this double,
Yes.
the
Mm,
following this complex would be exact.
mm.
I is 0, 2. So this complex, then this complex is exact.
That's absolutely true. Yes.
The condition of projection being 0,
Yes.
that this I is equal to 0, you understand? I mean, the third component
Mm-hmm.
is 0. So if the third component is 0, then
Ah,
our morphism lies in this.
it lies in here. Yes. Yes. But this is impossible because I must generate the whole of V. Yeah.
Yeah, but just we are quotient modulo the image of A, and then
Mm-hmm.
if this complex is exact, then it means it is 0.
Mm. Mm.
Point from the kernel of this projection morphism has zeros, the third coordinate equal to 0, and thus it's really from this exact complex. So it comes as an image of A.
As the image of what? A.
Of the morphism of A, yeah.
Yes. And so it's 0 in E.
Yeah.
Okay. Mm-hmm.
Thank you.
Можете еще раз переповторить эту дисциплину? Не очень слышно было вашу дискуссию.
So maybe then speak up.
Okay, so we want to prove that the restriction of the projection to E is an embedding. So this is true because okay, tensor O plus V tensor O plus O. Yes, so the third coordinate in respect to which corresponds to O is 0. And then this object, the representative of the homology must lie inside the exact complex. I mean, if you remove the third, this O into, then this complex is exact. Then it means that your point lies in the kernel, thus it lies in the image already. So it is 0. So the kernel is 0.
Спасибо.
Okay. Now if we have a function in our ideal, then it means that we have such inequality in particular, and it means that if we apply this function to B1 and B2, and then to the image of I, then we get just 0. Just for formally plug it into here, we get 0, 0, 0. Okay, and then conversely, assume f of b1, b2, I of 1 is 0. And then let's rewrite f of z1, z2 applied to the identity matrix as f of z1 minus b1 plus b1. So we just somehow expand it into well, series, or it's polynomial actually, with the origin in shifted to b1, b2. So we get f of b1, b2 plus something vanishing to the first order at b1, b2. Okay, for some for some matrix valued functions, C1, C2, and then we know that f of b1, b2 vanishes. So this vanishes, and this is z1 minus b1 times c1 of z plus z2 minus b2 times c2 of z. And now let's set u1 of z is c1 of z applied to I of 1. u2 of z is c2 of z applied to I of 1. So these are vector valued functions like here. And so we get f of z I of 1 equals z1 minus b1 times u1 of z plus z2 minus b2 u2 of z, and that's exactly what we had here. Okay, so it is equivalent, as we already mentioned, that to the fact that f of z lies in the ideal. Okay, so we established bijection between our well, monad represented sheaves E and the ideals J. No, J was sheaf of ideals. And we starting from this rank 1 torsion-free sheaf E, we obtained an ideal, J.
Just projecting E.
Just projecting. So in other words, as I said last week, we have this alpha isomorphism from E restricted to the infinite line to the structure sheaf at the infinite line. Okay, and it extends to the embedding from E like this, and the image of this embedding, well, let's call alpha tilde, the image of alpha tilde is J.
Why cannot we identify E and J?
Well, we can, but what we want to see is that any J can be obtained this way.
Is it true that here we want to restrict to A2?
Yeah, as always, yeah. The image of alpha, yeah, restricted to A2 is J. Mm-hmm.
So we can identify E with its image.
Yes, and we projected E. Well, it's just rephrasing what I said before. We have this projection, and as you explained, this is an embedding. The image of this embedding is J, but what we want to prove is that any J appears this way. So we constructed a morphism from M. We constructed a morphism like this. Namely, E goes to J. But we want to prove that it can be reversed.
J is an ideal of
Yes.
points? Or
Yes, absolutely, yes. Just because we know that it has second Chern class, second Chern class n, so it must be the ideal sheaf of n points. Again, from the same Euler heuristic argument, I have 0 goes to J goes to O, A2, but, well, you have to apply it to proper schemes. And then I have something of finite length n. Okay?
why is it of finite length?
Why is it of finite length? Because otherwise, the support, I mean, the support of the quotient is finite. Why? Because otherwise it would be some curves. But any curve on P2 intersects P1. You cannot have anything, any curve on P2 disjoint from P1.
And what's the problem with this intersection?
Because we had a trivialization.
Yeah. We know that the support of the quotient is disjoint from infinity because we have this trivialization at infinity. So there are no curves, there are just finitely many points, and the number of points just contributes to the second Chern class of this J.
Nice.
So our goal was to construct a backwards map, yes? A converse map
Yes?
from a sheaf on A2 to
Mhm.
torsion-free sheaf on P2.
Yes. And I start with any ideal, I consider the, well, I take this, and I take just B1 and B2 corresponding to well, let me say it better. Sorry. Now probably I can erase the monad. invariantly V is nothing but this ring of polynomials modulo G. It is n-dimensional space, and it is just this. Now, there is C times 1 embedding here. It is I. Okay, and there is multiplication by Z1, and it is B1, and multiplication by Z2, it is just B2.
And J is 0.
And J is 0, yeah, there is no J. Because of S1 condition and lemma. Okay, and the last thing I have time to say is that the Uhlenbeck space in this case is nothing but the symmetric nth power of the plane. And this resolution of singularities from Gieseker to Uhlenbeck is just the Hilbert-Chow map. Okay, so I wasted all my time today, as always, sorry. So we'll have to start Frobenius splitting after the vacations, so May 12th, yeah, May 12th. Yeah. Pardon me? Yeah, that's a very good remark that in this case, this is just empty. For when r equals 1, because you see S1 implies that j equals 0, and S2 implies that I equals 0. So if you impose both conditions, then there is nothing to speak about. No. So in general, there was just one irreducible component, and you just cut some smaller dimensional things with these two stability conditions. But in rank 1, those stability conditions cut out irreducible components and different irreducible components. So when you impose both, then you have nothing.
When n is positive, if n is 0, then we have some.
If n is 0, then I think the Hilbert scheme is empty also, right?
But there are vector bundles with zeros to check class.
I don't know, maybe it's some set theory question. I don't know, Hilbert scheme of 0 points. Is it empty or consists of 1 point? I don't know. I'd rather say it's empty, no?
Yeah, but n0, 0 corresponds to some vector bundles. To the vector bundles on your plane, yeah? And there are some vector bundles. All,
Yeah, there's an ideal sheaf, right? There is an ideal sheaf, just O inside O.
it's not, yeah.
It's just 1 point.
It corresponds to n equal to 0.
Yes.
Could you give
Thank you.
some literature on this topic?
On this topic, well, this is the best possible reference. Book by Hirako Nakajima, lectures on Hilbert scheme of points on surfaces. And it's in the very beginning. It's the whole book, but the whole book is advanced, and we only studied the very second chapter.